So a chemist called Soren Sorensen, I believe, actually came up with the definition of pH, and he was a brewer for the Carlsberg Corporation, and they wanted to make beer the same way every time, and so one of the things that he had to invent is a way to measure the acidity of the water used to brew the beer. So he defined pH. And pH, actually, no one's really quite sure what it stands for, so we normally just say it doesn't stand for anything. But he defined it as the negative base 10 logarithm of the concentration of the H plus ion. And so it's a logarithmic scale. You can also undo this if you want to know the H plus concentration from the pH. This is very useful to sort of commit to memory. The H plus is 10 to the minus pH. That's very, very handy. So for instance, if you've got an H plus concentration that is 1 times 10 to the minus 7, then the pH of that is the negative log of 1 times 10 to the minus 7, and that turns out to be minus 7, but actually when you flip the sign through our definition there, that becomes 7 on the nose. And so that's why we have a negative in front of there, because these tend to be quite small values. If you take the log of a small number, you get a negative value. So we normally just go ahead and flip the sign, and that makes everything nice and positive. Now, rules of significant figures here, it's not terribly critical, but the number of significant figures in the value you take the logarithm of becomes the number of decimal places. So a 1.0 times 10 to the minus 7 has 2 significant figures. If you recall, the times 10 to the power doesn't change the number of significant figures. 1.0 though, ones are significant, zeros are if they're after a decimal, so that gives us 2. So we need to have 2 decimal places here, and so 7, which is what our calculator will say, should actually be written as 7.00. And again, if you look at this definition here, 10 to the minus pH is H plus, so 10 to the minus 7, right, that's just the same thing as this number right here. So it works in both directions. We can go ahead and do an example pH calculation. So maybe we've got a solution with an OH minus concentration of 8.3 times 10 to the minus 6 moles per liter, and we might want to know what the pH is. And so we know the pH is the negative log of the H plus concentration, so we're not given the H plus concentration, we're given the OH minus concentration, but we can find this because we know Kw is 1 times 10 to the minus 14, and it's a constant for water at room temperature, and it's equal to the product of H plus and OH minus. And so we know this, and we know this, and we're given this, so we can solve by dividing both sides by the OH minus concentration. And the reason for that is now it cancels out here and leaves us with what we want to know. So the H plus concentration is 1 times 10 to the minus 7. 10 to the minus 14 over the OH minus concentration, which we're given 8.3 times 10 to the minus 6. The convention here is to leave off units till we get to the very end. Significant figures, we have 2 and 2, so our final answer is only going to be good to 2. So that gives us 1.2 times 10 to the minus 7. And it's a concentration, so moles per liter, or capital M. And then we want to find the pH. The pH is the negative logarithm of the H plus concentration. So now we've solved for it, 1.2 times 10 to the minus 7. We can't take the logarithm of anything with units, so we just leave the units off by convention. And when we do this, we get 6.92. pH doesn't have units, but again, remember, the number of significant figures becomes the number of decimal places, and so 6.92 would be as good as we could write that answer down. For pure water has an H plus concentration of 1.0 times 10 to the minus 7, and we've seen that this has a pH of exactly 7, and we know earlier that pure water is exactly neutral. We can also go ahead and kind of draw out the pH scale, and so we know that 7 is a midpoint, and this corresponds to neutral. What we find is that when we increase the H plus concentration, we decrease the pH, and so pHs less than 7 are acidic, and pHs that are bigger than 7 are classified as basic. And technically this only applies to room temperature, and we'll just sort of assume from here on out we're always working with room temperature. But if you're dealing with a human body that's a little bit warmer, neutral pH is actually somewhere on the order of like 6.82, and if you're working maybe at very cold environments, the pH might be a little bit higher for neutral, but we'll almost always presume we're at room temperature where a pH of 7 is exactly neutral. The H plus concentration for neutral is 10 to the minus 7. and the pH scale is logarithmic. And what that means is that as we increase the concentration, so if the blue here represents the concentration of H+, if we make it 10 times bigger, so 10 to the minus 6 molar, the pH goes from 7 to 6, and so it changes by a whole unit. So when the pH goes down by 1 unit, the solution gets 10 times more acidic. If we go ahead and we multiply that concentration by another 10, and so we make it 10 to the minus 5 moles per liter, and we calculate the pH of that, it is a pH of 5. So it doesn't look like much, right? So we've increased the concentration by 10, the pH dropped by 1. We've increased it by another 10, so that's 100 times more acidic than pure water, and the pH changes by 2 units. So pH is a logarithmic scale, and that means that very large changes in concentration give rise to quite small changes in pH. And if we go the other way to basic solutions, so if we make the H plus concentration 10 times smaller, now it becomes basic, and if we calculate the pH of there, we'll see 8. And so on. If we make the H plus concentration 10 times smaller again, so 10 to the minus 9 molar, we've divided that by a factor of 10 if you like, the pH goes up by 1 unit. So again, we can see it's basic when the pH is greater than 7, and it's acidic when it's less than 7, and each change of pH by a unit corresponds to a change of H plus by a factor of 10.